And here we are. Once again, it's the physics video lecture. Physics 107B, video lecture 9. We're working on electromagnetic waves, Maxwell's equations. So let's see where we were last time. So electromagnetic waves. Last time we had from, that's right, electric and magnetic fields both satisfied a wave equation, which I'll just write as d squared phi dt squared del squared phi. So each one of these 6 components satisfies this wave equation. C here is 1 over root u naught epsilon naught, and it turns out to be 3 times 10 to the 8 meters per second. We then went to discussing waves on a string. Okay. And this is a good exercise because we can visualize exactly what's happening, and we've seen these phenomena before. So we're on a string here. We have the positive z-axis, and we've seen this kind of thing, standing waves or traveling waves. And they're transverse waves. So f of z and t, which was a cosine kx minus omega t plus delta, was a transverse displacement of the string from the just straight line. So transverse displacement. So we had a good idea that things could be displaced perpendicular to the direction of propagation. Then we had a wave number, 2 pi over lambda. You just see that by the periodicity of the cosine if you hold everything fixed. We had omega over k is the wave speed v. Delta was just a constant that will give us the degree to which this sinusoidal pattern is displaced. So that makes, we don't have to write sine or cosine or a combination of 2, just cosine, and then the delta will displace the thing. And what else did we have? Okay, good. So far so good. We had also seen that k plays the role of a vector in the sense that we can reverse the sign of k and have a wave traveling to the left instead of this one, which is traveling to the right. Okay, so what we're going to do next is introduce the complex expression for the wave, which makes them very easy to work with. So next, complex numbers. In particular, we want e to the I theta cos theta plus I sine theta. That's what we want to make use of. And maybe I should also state generally z x plus I y, z star, the complex conjugate, x minus I y. And you can also identify this as the real part plus I times the imaginary part of z. So just referring to this one. And then just based on these definitions, you of course have the real part equals z plus z complex conjugate over 2, and the imaginary part, z minus z complex conjugate divided by, okay, not so fast. Imaginary part of z, z minus z complex conjugate divided by 2I. So of course that's all standard, but it's going to allow us to add, to first of all express this as part of e to the I something, and then add and subtract these functions very nicely. So that allows us to write f of z is equal to the real part of a e to the I delta. I'm going to bring those, yeah, and then e to the I kx minus omega t. So the phase constantly gets pulled into this complex amplitude. So we can't just dispense with the, well, we'll see as we go along. Sometimes we have to be careful about what's, the real part and what's complex. And other times when we're just interested in dispersion relations and stuff, we kind of ignore the fact that we're taking the real part, okay, but it's there. And we can also use the nomenclature that this tilde here is going to indicate that it's the complex, by the way, this is z and t, it's the complex form, and then we can have the a tilde e to the I k z or x. Well, I was using x last time, going with the book and using z, so let's see if we can maintain that. Kz minus omega t, right? So we're looking at x, y, z, that type of situation. Yeah. If we don't care in certain situations, we just drop the tilde and just deal with it. But strictly speaking, we have that phase information in the complex amplitude, so it can be important. Okay, what's next is the summation of these. So we can sum a whole bunch of these waves and still have a solution to our wave equation. Okay, just linear operators. And do I have, just for the record, yeah, I have that here. Am I using C or V? Okay, for Maxwell's equations, we were using C for the speed of electromagnetic waves. For this wave, which is to say this one, we'll probably be using V. So we'll have omega is equal to K times V, like, or V times K, better yet. V times K for this type of thing. So yeah, we're talking about a wave on a string, but of course we're looking towards the electromagnetic waves coming right up. So right now we're still working with waves on a string, and we're going to sum these under an integral sign. And one of the things about the complex notation is that you can take the real part of the sum, so you do all your summations, and then of the complex numbers, then you just take the real part of that. And true for all linear operations, you can just interchange those two. Okay. So we don't have to worry about any taking of the real part until, say, the end of an operation where we're actually asking for that. So next we're going to sum these waves. So the general solution of the wave equation is going to be f of z and t. Still got the tilde there, you sure? It's going to be the integral, and this a tilde now depends on k e to the I k x minus omega t dk. So each individual one of these, just think we summed them all up. Could have been actually a sum, and we could have had integer values, but we'll do the integral. And strictly speaking, it could be from 0, negative to positive infinity, with omega is equal to omega of k. Remember, in the simplest case, it's just v times k. Okay, so omega is definitely a function of k. And there's an interesting homework assignment that we're going to do. Problem 933. And that is, how do you extract the a tilde of k here? It's a Fourier transform, but we have integration in x and t. So I'll give a couple of tips for that right now. So what we're going to show is, I'll write down what our answer is. A tilde of k is equal to 1 over 2 pi. These are all from minus infinity to plus infinity. F of z and 0 e to the minus I k z dk. K of dz plus 1 over 2 pi minus infinity to plus infinity I over omega f dot z and 0 e to the minus I k z dz. So this is an interesting problem because we're specifically looking at the real. Okay, this was the complex f. This is the real part. This is also the real part of f dot. And we had, just starting with this expression here, f tilde of z and 0 equals, of course, just writing this down where t is equal to 0, right? So a tilde of k e to the I k. I gotta make up my mind with the x's and z's here. This was z. Yeah. Kz dk. Right? So the t was just 0. And then f tilde of Zn0 complex conjugate, you have to take the complex conjugate of this whole thing. Okay. Same thing for initially the f dot here. The f dot, that refers to the time derivative. Okay. So the f dot tilde of z and 0 would have also been obtained by the time differentiation of this thing evaluated at time t equals 0. Okay. So you do something similar there, and then you also f dot tilde of z and 0 complex conjugate, you do something similar. Okay. Now everything's up here. So to extract the actual expressions without the complex conjugate over here, or without the complex, right, the actual real core there, real part, you make use of these relations right here. So you're going to have 4 of these expressions, and you have to do the Fourier inversion. Yes, one more thing. So note, you have to make use of the Fourier transform. So I'll just write the general Fourier formulas down for the integrals. You know, if you have a phi of x, or am I using z, I'll just write x now. So if you have phi of x equals integral phi hat of k, that's your transform, e to the I kx dk, right? So your argument is x. Then your Fourier transform is 1 over 2 pi. These integrals are both minus infinity to plus infinity. Phi of x e to the minus I kx dx. Okay. So putting all those things together, you can finally derive this expression, which is good practice. Okay, good practice in the whole thing. We're going to continue on with this, the meaning of this object here. Yeah, so this was just a note on homework problem 933, which works with this, okay, this stuff here. But yeah, let's continue on with the discussion of that solution of the wave equation. It's just a linear combination of solutions that clearly are solutions. So I'll do this in maybe 2. I'll split the board. So we have a traveling plane wave, and that solves the wave equation, and that was the original Fourier component. So F equals A e to the I kz minus omega t. And since we're on the string there, did I say plane wave? We're not there at plane waves yet. We're at the wave on the string. We'll just say traveling wave. But in this form, it fills all of space. Okay, so we have to imagine this thing going from plus infinity to minus infinity. Fills all of space. Or in this case, space is our z-axis of it. What I'm driving at is we can get something more localized with this thing here. So what we're looking at on this side of the board is the wave packet. localized. Okay. So that's one of the things we can do with this type of an integral formulation. And you can actually see this on a string. You have a long string and you're sending waves down it. Of course, they're also bouncing back, but you're sending waves down it, and it's just a uniform picture all the way across. On the other hand, if you were to pluck a string or a rubber band or something, you can get a pulse. You can actually see a pulse traveling. And we're going to identify that pulse with a wave packet. So it's a pulse of some type, still obeying the wave equation, and that will be this f tilde of z and t equals, yeah, that same thing up there. Let's see if I want to say anything about that. Well, yeah, I'm going to work on that. Yeah. So yeah, let's go ahead and use that thing there. So I'm just copying that down. E to the I k z minus omega t. Okay. So how can we recognize this or see it as a pulse, as a localized wave packet? If it is a wave packet, then the localization will also show itself in that this A of k is somewhat localized. Right? The A of k is localized as well, so that there's a greatest contribution from some place along the k axis. So we will have, if it's localized, so let me go ahead and write this. If localized, then A tilde of k will give its greatest contribution around k sub 0, say. Gives the greatest contribution to the integral around k equals k sub 0. Okay, so that's what it'll mean to be localized. This function will somehow be peaked around k sub 0. This one right here. So what we can do then is expand this in the following way. So now write this one needs a little room. We'll send this up here. I'm just going to expand that phase out in a certain way. I'll make sure I have enough width here. So yeah, kz minus omega t, so now write kz minus omega t is going to be equal to k0 plus k minus k0 times z. That's trivially true. This one we're actually going to expand. Minus omega of k0 plus d omega dk evaluated at k0 times k minus k0 times t. So this expansion here, which we're saying we can do because the greatest contribution is happening around k0, and then k minus k0 doesn't have to be small, but it'll be, mostly small, close to k0. So this goes into there. So we have to write the whole thing out. So that our integral tilde of z and t is now this a tilde of k e to the I, and yeah, we'll go ahead and write this out. Exactly what I have up here. Could just kind of point at it, but we'll just write it out. K0 plus K minus K0. Z minus, do I need another parentheses? Omega K0 plus D omega dk K0. K minus K0 T. Okay. So what we're going to do is bring out the e to the I K0z, right? These are exponentials, so we can use that multiplicative property. K0 is a constant, okay, and we're integrating over k. So we can pull out following. E to the I K0z minus omega of K0 T. Okay, I got the parentheses right, so minus omega of K0 T. That can actually come outside the integral. Minus infinity, plus infinity, and then whatever's left. So a tilde k. Now we have e to the I k minus K0, we can factor out. And what's left with is z, k minus K0 here, minus d omega dk K0 t, close parentheses, this is in the exponential, and then dk. Okay, so what have we accomplished here? What we're now going to look at is, and that'll fit on the bottom of this board, now consider the f tilde of z and t, where we take the square of it. Remember, this is a complex quantity, so it's f tilde times its complex conjugate. That's what this expression is squared here, equals, let me go ahead and send that up there, equals a little room to evaluate this. Okay, here we go. We can point to everything that we need. Forget this, we'll rewrite it. So now, f tilde of z and t, complex conjugate, and multiplied by its complex conjugate. So if we do that above here, this times its complex conjugate is just equal to 1. Okay, so there's just a 1 there. And so yeah, leave some room, or put this in your notes. This here, complex times complex conjugate, is 1, because, right, magnitude of 1. What we're left here, if we take this integral times its complex conjugate, we're actually left, since we're integrating over the k, we're left with just some function, which I'll call phi for lack of a better word. We're left with some function of z minus d omega dk times t. Phi of, because we're integrating over it, so phi of z minus d omega dk times t. Of course, that solves a wave equation with this as the speed. So this is called the group velocity. That pulse that we were talking about is transmitted along the line, and it generally, the wave packet travels with the group velocity, which is that, okay? So equals phi of z minus v group t, right? Taking us back to the original form that we were solving our wave equation with. We're just saying that that equation has that form because of this argument here, because you're integrating over all k. You're left with a function of that form, and vg equals d omega dk is the group velocity. Very important concept, and under other conditions, this generalizes to v group is equal to d omega d vector k if you're in 3 dimensions. Okay. Good, so yeah, group velocity, very important concept. This is the velocity with which, say, a signal or with which energy is transported. Oh yeah, then I should also mention the phase velocity. The phase velocity is just v phase is equal to omega divided by k. Okay, great. Let's consult the clock now. Okay, so we're going to return to our electromagnetic waves now. And the Maxwell equations. So, turning to Maxwell equations in vacuum, remember we had divergence E is equal to 0, divergence B is equal to 0, curl of E is equal to, let's get the minus sign there, dB dt, that's right, minus dB dt, curl of B is equal to u naught epsilon naught dE dt. So those are the equations that we saw. We plug them into each other, we got the wave equation. So now we're returning to those. And of course, for any component of E and B, we have d squared phi dt squared is equal to c squared del squared phi for any component. So now we can take those traveling waves that we were looking at, and let's see, we're using z. So we'll be clear on that. X, Y, and Z. And we'll write these down and then leave them up to work with. So these are the complex ones. They've got the tilde there. We've got an E0 vector, again, complex e to the I k z minus omega t. And we have the same thing for b. Z I didn't need right there. Oh. So e tilde vector of z and t. That's the idea. So b0 tilde e to the I k z minus omega t. And we know that omega is equal to ck. That is good. Good, so we're going to hold on to these. I'll send them up here. And now, so I just wrote those down. Do they, first of all, solve the wave equation? They should. We'll check real quickly. And second of all, do they solve Maxwell's equations? And more importantly, how do they solve them? Okay, so that's what we're going to do next. We have Maxwell's equations up there. We have these plane wave solutions, traveling wave solutions. So first of all, solutions of wave equation. That should be pretty basic. We take two time derivatives and we bring minus I omega squared times everything, and then we're saying equal to c squared, and then we'll have an ik squared. We're only going to have the two derivatives in z there, so ik squared, and minus I squared is -1, I squared is -1. So yes, we get omega squared equals c squared k squared. So yeah, there's solutions. Next, what about Maxwell? Well, that's where they came from, so they should of course work. But there's a little more to be had. So let's consider the divergence of E. Divergence of E equal to 0. And what that means is dEx dx plus dEy dy plus dEz is equal to 0. Now if we take this expression here for our wave traveling in positive z direction, dEx, so derivative with respect to x is trivially 0. And here we also have respect to y is 0. Derivative with respect to z, we're looking at e sub z, 0, but I'll just forget, times ik. And that can only mean that this has to equal 0. And that's really important. It means that our field vector only has transverse components. Remember, the direction of propagation is the positive z-axis. We don't have a z component of the field vector. That means we have E is a transverse wave, and the very same thing is going to hold for B, divergence of B being 0. So likewise, B is a transverse wave. Okay. E sub z identically equal to 0, B sub z identically equal to 0. So that's where we get the fact that the electromagnetic waves are transverse. Of course, we've been studying those in our strings, so we can visualize them immediately, such as it is. Good, so yeah, we've got the transverse waves. That's an important result. So what about Faraday's law? Curl of E equals minus dB dt. That's actually going to give us a connection between the electric and the magnetic field. So both of these field vectors solve the wave equation, and we've seen that they're transverse waves. So now we'll get the relation between those two. And yeah, I can send this up here. I don't really want to erase these, do I? Oh, okay. So let's just go ahead and, well, we can do this right here. So the curl of E, we're looking at a vector that would have D, so the X component, dy ez minus dz ey, and cyclic. Is that how I did this one? Yeah, and cyclic. So, and then the y component dz ex minus dx ez, and the z component dx ey minus dy ex. And this is going to be equal to, and I'll do the equality right underneath here, minus dx dt minus dby dt, comma, minus dbz dt. So good, yeah, we can evaluate these here. So there's derivative with respect to y, we can start striking these, is, I'll write these directly underneath. So what do we have here? dz with respect to ey. That works. That gives us just ik ey. dz with respect to ex. dx with respect to ez goes away. So this one gives us ik ex. This one has a minus sign. And then this one right here, these two derivatives trivially vanish. Okay, they're not there. So that's this vector. 0. And over here, we would have always just a minus I omega. So minus minus I omega. So minus minus is plus, so it's just I omega dx, I omega dy, and bz we didn't have, so it's 0. So we're going to equate these two vectors, and we'll see the relation between them. First of all, we see that the E field and the B field have this reversed relation there with the x and y. That can be expressed as follows. I think I'll do it directly underneath, and then we'll ponder it. So yeah, the i's cancel, and then divide by omega, we'll have k over omega. On each of those, good. So what we can get out of this here, I'll just write it down and we'll look at it. We can get b 0 tilde the vector k over omega z hat cross e 0 tilde the vector. And the picture is in order. With this same orientation now, we'll go ahead and write it in. What we'll do is we'll let E be along the x-axis, and then z hat cross E, z hat cross the x-axis will be in the y-axis direction. And yeah, this relation just by virtue of the cross product, okay? So what we get is the following. We'll do this picture from the z, x, and y direction. So if our E field is going to be like that, here we can use a different color, then our B field is going to be like so. And I'll fill in to get a little perspective. So our E is going like this. And then our B field is like that, and then in the minus direction. So that's how E and V propagate. Yeah. I'll even put this here as a note. You've got your I hat, J hat, K hat. This is determinant rule. 0, 0, 1, and EX, EY, EZ, 1. Where K hat is Z hat. Maybe I should write X hat, Y hat, Z hat. X hat, Y hat, Z hat. So that is exemplified right here, and that's what we get out of that. So I'm just going to do one more thing and generalize this to arbitrary direction. So yeah, this is E, this is B, and that's that relation. So finally, let n equal k over k. So this is the unit vector pointing in the direction of the wave vector k. Then we can generalize these things immediately. Then E is equal to E0 e to the I k dot r minus omega t. And B is going to have this same relation, except instead of Z hat, we'll say N hat. Oops, here, look at this. Yeah, let me wrap this up with now we turn this into E of R and T. Okay, it's really the same wave phenomenon exactly, except now directed arbitrarily in space. So this one we can leave the vector off here, tilde, and say that it's in the n hat direction, defined right here. And then for our magnetic field, we've got B0 and e to the I k dot r minus omega t. And now the direction is the generalization of this, so it's just the n hat. So we've got k hat cross n hat. K hat cross n hat equals 1 over C. I'm going to have to check this actually. K hat cross E tilde vector. And then on dimensional grounds we see B is equal to E over C, okay? Because these are actually, I'm going to be careful there. E equals EK. There's the direction of E. Okay, good. Let's leave it at that. We'll return to this. Yeah, we have omega is equal to C times K. C times K. We have K over omega. K over omega is 1 over C. Yeah, K over omega is 1 over C. This should actually be n hat. If we have a 1 over C, right? K over omega, 1 over C, 1 over C, n hat cross E. This one looks to be right. B over C. Okay, good. We'll leave it there and pick it up next time. See you guys later.